Hello everyone, and welcome back. Today we're going to continue our exploration of R programming and focus on how to do some of the more common problems associated to continuous probability theory. So let's start off with probably one of the most easiest to work with probability density functions, and that's going to be a uniform probability density function, which I'm just going to be typing uniform PDF. So let's assume that we want to choose a random number x from a uniformly distributed distribution. So in order to choose a random number, you will do r and then unif for uniform. So a random number from a uniform distribution. And let's assume that we just want to choose one number. And let's assume that we want to select a random number from, say, 0 to 10. So if we give that a run, that's going to be defining a random continuous number from 0 to 10. In this case, it's approximately equal to 1.12. Now, obviously, if we give this another run, that's going to give us another uniformly distributed value. If we run it again, and run it again, and run it again, that's going to give us several different values. Obviously, if you want to sort of simulate some reproducibility experiment, you'd most likely want to set, for example, a seed before you get started. So, for example, you can set seed to be equal to 22, and then select that particular random number, and obviously we see that x is equal to 3.04, and then we can run it again, get another one, but obviously if we reset that seed, we're going to get the same exact uniformly distributed random number from 0 to 10, just like we started with, just in case you want to sort of reproduce that experiment that you just ran. So now let us choose a random set of numbers from a uniform distribution. And let's assume that we want to choose 100 numbers. So let's assume that we want to select 100 values from the interval 0 to 10, right? And that's going to choose 100 numbers, and if we want to display that, we can just run that function that's going to display all of our numbers that it has selected, right? So in case you do not already know, the expected value of a uniformly distributed random variable from 0 to 10 is approximately going to be equal to 5. So if we take the average of all of these values, we should be getting something close to 5, right? Provided that this is a large enough sample set. So obviously one way you can sort of graphically display this is to construct a histogram of the values in S1. And if we give that a run, notice that we, in some sense, have about the same number of individuals, say from 0 to 1, 1 to 2, 2 to 3, and so on. Obviously with a few less from the 5 to 6 interval, but obviously if you increase this sample size m, hopefully that should equate approximately to a horizontal distribution. Obviously, we can test to see what the expected value is, because we know that the expected value of a uniform is going to be equal to the lower endpoint plus the upper endpoint divided by 2, which in some sense is the median, right? But obviously, if we do, our particular data set and find the mean of it, so if we do the mean of S1, we're obviously not going to get something exactly equal to 5, but usually the larger the n is, on average, the closer the sample mean of a random variable would be closer to the theoretical value. Right, and obviously we can look at the variance as well. So if you remember that the variance of a continuous uniform random variable, this is going to be equal to b minus a squared, so b minus a, the quantity squared, all divided by 12. And in that theoretical case, that's going to be equal to 10 minus 0, the quantity squared, divided by 12, which obviously is equal to 8.333. And if we do the sample variance of S1, we should be getting something hopefully close to what the theoretical value actually should be equal to. And one could agree that it does appear that our sample set at least is approximately a uniform distribution with respect to the mean, variance, and also the histogram that has been generated. So let's just go ahead and do a couple probabilities on this uniformly distributed random variable for the theoretical case, right? So not for our sample. So let's assume that we're interested in doing the probability that x is less than 6, and let's assume that we're again having a lower bound of 0 and an upper bound of 10. So in this case, we're going to be using the function that's already predefined for us, which is going to be p unif. So that's probabilities on the uniform distribution, and we want to find all values that are less than 6, right? Actually, let's make this 6.1 just to make this a little bit more interesting. So you're going to be typing in 6.1, and then you're going to be typing the lower bound, which is going to be 0, the upper bound, which is 10 for that random variable. Obviously, this is associated to a lower tail. And that's going to show that 61% of the data is less than or equal to 6.1 on the interval from 0 to 10, which obviously from the geometric perspective is correct. Now, if you want to do, for example, the probability that x is, let's say, greater than or equal to 7.3, then that's going to be p unif. You could do 7.3, 0 to 10, and then we can do just lower tail is equal to false, and that's going to give us that answer, or you could approach this from the complementary perspective in case you want. And obviously, if we want to do something like the probability that 2.1 is less than x is less than 3.2, you can obviously do, for example, an upper tail or an upper probability minus a lower probability, like we typically do in calculus. For example, you can do p unif of 3.2, 0, 10, lower tail equals true, minus p unif of 2.1, 0, 10, lower tail equals true. They should match, either both true or both false. And that gives us the probability of interest. The last thing I want to show for the uniform distribution is how to do quantiles, or some people will refer to these as lower percentiles. So lower percentiles. And for example, let's assume that we're working on the interval, let's say 6.3 and 54.3, and let's assume that we're interested in the 34th percentile, right? So the 34th percentile. So in order to do this, since uniform is a widely used distribution, this function is already predefined inside of the base language of R. So for quantiles, we're going to be using Q, UNIF, and you're going to see a lot of patterns here with a distribution that's already predefined in R. You're going to have P distribution, Q distribution for probabilities and quantiles of that distribution of interest, and the quantile we want is going to be 34, lower bound 6.3, upper bound 54.3, and obviously we are focusing on a lower percentile, so lower tail is going to be equal to true. If you want, for example, a upper 34th percentile, you would just say lower tail is equal to false, and that will give it to you. So in this case, we have that the 34th percentile for a uniformly distributed random variable on 6.3 to 54.3 is equal to 22.62, and those are the basics for continuous uniform distributions in R. The next distribution that we're going to look at for the continuous probability discussion is going to be the exponential probability density function, right? So we know that the exponential distribution is continuous, exponentially decreasing on the interval 0 to infinity, right? So let's choose a random number from an exponentially distributed distribution. So to choose a random number, we're going to be doing R for random number and then EXP for exponential distribution. We're going to be choosing one number, and then we're going to be giving it the rate parameter. This is going to be equal to the lambda in the typical definition of the exponential distribution. And obviously we have a random number chosen to be equal to 0.89. Obviously, if you want to do some reproducibility studies, you should be studying seeds for all of these examples. Now let us assume that we want to collect a sample. Let's call it, for example, S2, and let's assume that we want to draw 100 individuals from an exponential distribution. So we're going to be doing REXP for a random number, in particular a random set of numbers. Let's select 100 values, and let's assume that we're working with the same rate parameter, 0.35. And again, if you don't know what this rate parameter lambda is, that's just 1 divided by the expected value. So if you have, for an example, an expected value of 50, the rate parameter is going to be 1 divided by 50 in that case. So here, we're going to be selecting a random sample of size 100 from an exponentially distributed random variable. We can take a look at this and see our empirical exponential distribution. Obviously, it appears to be approximately monotonically decreasing, but obviously, as I increase the sample size, it's going to be more and more closer to an exponential distribution, right? So, for example, if we take this and we consider the mean of S2, we're going to be getting 2.86999, right? And you can ask, well, what's the theoretical mean of this distribution? That's going to be equal to 1 divided by our rate parameter, which is 1 divided by 0.35. And notice that these values do appear to be very, very close. And if I were to do the sample variance of our sample, we get 8.22. And the theoretical variance is going to be 1 divided by 0.35, the quantity squared, which obviously appears to be at least close enough, I guess you could say. So those are some of the basics for exponential distributions. Now let's do a couple probability examples on how to do probabilities for exponential PDFs in R. So let's assume that we're interested in finding the probability that x is bigger than 2 with the prior knowledge that the expected value is going to be equal to 1.23. So in order to do this type of problem, we can, for example, first off define our lambda value. So lambda value is going to be equal to 1 divided by the expected value of 1.23. So that's our L. And then we can use the function p for probability and then exp for exponential. So the probability value that we're interested in is the probability that x is bigger than 2. So this is going to be equal to 2. And then the rate parameter, which is going to be equal to 1 divided by the average, or L as we've already defined that. And since we're looking at the upper tail, this is going to be lower tail is equal to false. And that is the associated probability. If you want to find, for example, the probability that x is between, let's say 3.4 and 4.5, and let's assume that we know that the average is equal to 4, then what can we do? So we can do, for example, p exp of 4.5, rate parameter equals 1 divided by 4. We can do lower tail is equal to true, so that's the upper bound, minus p exp 3.4, same rate parameter, and then again lower tail is equal to true, and then it's going to give you the area between these two locations on the horizontal axis with respect to this particular exponential distribution. And what else can we do? So we can find, for example, quantiles or percentiles, and percentiles for an exponential distribution. So for quantile, what did we use for uniform? We used Q, so we're going to be using Q, exp for quantile. Let's assume that we're looking for the 21st percentile for this exponential distribution. So that's going to be a rate parameter. Let's assume we're working still with 1 over 4 just for consistency. And if we're looking for a lower 21st percentile, lower tail is going to be true. So that means 21% of the population has an x value less than or equal to 94. And we can sort of switch this around if we need to. So what is the upper 85th percentile? So the upper 85th percentile is going to be equal to what? So if we're looking for upper percentiles, we're going to be doing lower tail is equal to false. And this says that 85% of individuals have an x value bigger than or equal to 0.81. So those are some of the basics for exponential distributions in R. The next special distribution that's already defined in R that I want to introduce is probably the infamous normal distribution, and of course the standard normal or Z distribution will be a special case of the normal distribution in this example. So let's assume that we want to choose a random number from a normally distributed population. So again, this is the normal distribution. And we're going to assign this a value of x. And just like before, we had our unif for a uniform distribution, our exp for an exponential distribution, and here we're going to be doing our norm for a normal distribution. We're going to be choosing one element, and let's assume that we're sampling from a distribution whose mean is 125 and its standard deviation is 1.2. So this probably sort of looks like a blood pressure distribution or something of the sort. So that's going to give you a random number selected from this particular type of distribution. Let's take a look at how to gather a sample from this normally distributed population. Obviously, we're going to be doing our norm again, and obviously the next thing we're going to be specifying is the sample size. Let's assume that we're sampling from the same exact distribution, a mean of 125 and a standard deviation of 1.2. Obviously, you can change these to whatever application you're working with. Let's take a look at the histogram just to sort of see what this looks like, and that's sort of what our histogram looks like. Obviously, the larger the sample size, hopefully, the more closer and closer this is going to look to a normal distribution. Obviously, if you do not like the number of classes or sets that it's partitioning your histogram into, keep in mind, in case you do not remember, we can input an actual manual function to sort of tell it to partition this data set into a certain number of breaks. For example, we can do 20, we can do 200, and that probably is going to change the shape of what your histogram is so that, whatever it sort of defaults to is not giving you any misleading advice, right? But obviously, the larger the number of breaks, the smaller the frequency in each of those breaks. So obviously choose the breaks manually with careful consideration. So obviously we are sampling from a distribution with mean 125 and a standard deviation of 1.2. So therefore, if we take the mean and standard deviation of this distribution, we're not going to get exactly 125 and 1.2. Like the mean here is 124.9948, which is arguably close to 125. And the standard deviation typically is going to be farther away than that of the mean typically is. But notice that when we take the standard deviation of sample set S3, notice that we have a standard deviation of 1.1974, which one could argue is close to 1.2. But obviously, that's our sample mean and sample standard deviation, and that's our population mean and population standard deviation. So let's assume that you want to do probabilities under a normal distribution. You would do the same exact style as we did for the other two examples. So let's assume that we're interested in the probability that x is bigger than 123. So you select one individual from this normally distributed data set. What's the probability that their blood pressure is more than 123? So that's going to be equal to p norm. And then the value of interest, we're going to be associated this to a population mean of 125, a standard deviation of 1.2, and we're going to be looking at the upper tail of this distribution, so we're going to be doing the lower tail is equal to false, since we want greater than 123, not less. And we have about a 95.22% chance of selecting an individual whose blood pressure is bigger than 123. And obviously, another thing you can do is example quantiles, which would go in the same exact style as before. Instead of p norm, we will be doing q norm. Let's assume that we're looking for the lower 25th percentile. So we're going to be doing 0.25, the mean of the distribution you're interested in, the standard deviation of that distribution. And if you're interested in the lower 25th percentile, that would be lower tail is equal to true. So this means 25% of this population has a blood pressure of 124.19 millimeters of mercury or less, right? So that's pretty much how you would do quantiles, probabilities, and sampling for normally distributed populations in R. The last thing I want to show you in regards to continuous probability theory in R is how to create your own probability density functions and also how to find probabilities associated to them. You also can find quantiles of your own probability density functions in R, but it requires a couple other functions, which I'll talk about in another discussion, right? So we're just going to be talking defining PDFs and integrating those PDFs inside of R, right? And obviously you can learn how to do just some arbitrary integrals of functions as well using practically parallel implementations. So obviously there are several other packages you can install into R if there are some special functions that are not defined in your base package. For example, the log normal distribution probably is a function that has already been implemented either in base R or in a package for which you can install. But generally in practice, you're going to be working with population distributions that you probably have not seen already defined, or probably has not even been created or studied in any serious fashion in the R community, right? So you would have to define your own, and still you probably would be working with, probabilities and quantiles for that distribution. But I'm just going to be using the log normal distribution since it's pretty common, and sort of show you how to sort of define your own probability density function, do probabilities on it. So for the log normal distribution, sort of like the normal, where the normal we usually are given the mean and the standard deviation, log normal, if you're giving the median and the mode of the log normal distribution, typically those are the easiest parameters to know and also to work with. So let's assume that we have a median of 5.4, let's say the length of your hair strands, and a mode or a most frequent value of 4.2 in terms of the length of your hair strands, right? And obviously there's some transformation parameters A and B, which are going to be used in the implementation of the log normal PDF. If you do not know what these are, that's perfectly okay, but these are sort of associated with theoretical understanding of the log normal PDF. So, in order to define an arbitrary continuous function in R, what we're going to be doing is first naming your function. I'm going to be naming this function fx. Some people use f capital X, but in R, unless you've changed your base text, little x and capital X sort of look the same. So I just use little x for default, since it possibly reduces the number of mistakes you can make when you start to code longer functions. And this is going to be a function of one variable only, so it's going to be function open parentheses x, and then it's going to be the body of this function, so where we're pretty much going to be defining what that PDF actually looks like. So the log normal PDF is given by 1 divided by x times the parameter b times the square root of 2 pi, all in parentheses. That's the leading coefficient that allows the area from 0 to infinity to be equal to 1. And then we're going to be multiplying this by e to the power of minus, and there's a couple ways you could implement this. Let's do it this way. Let's do minus 0.5 times, so it's negative 1/2 times something squared, right? So that something is going to be the following. So the thing that we're going to do first is natural log, or log of x, that's defined to be equal to the natural log by default, minus the mean, which is going to be equal to a, all divided by that constant b, and then we're going to be squaring that term, right? So the natural log of x minus a over b, the quantity squared. Here a is sort of acting like the mean and b is sort of acting like the standard deviation, but aren't actually those terms, which is why I'm not defining them that way. But once you define this, you just have to run the leading line of that function code, and that will define that function for you, and you should see it defined up here in your R environment. So if everything is perfectly working well, then you should be able to integrate this function. For example, if we want to integrate this function f of x, and if you do know anything about the log normal PDF, then you should know that this is defined on the interval 0 to infinity. So if we integrate from 0 to infinity, which you can do via this line of code, then you should get a value of 1. Now, when you use the function integrate in R, it's going to say with absolute error less than something, something, something. As long as that number there is pretty small, you won't have to worry, because this function integrate is a numerical integration method. Obviously, some functions behave a lot more better than others, so the numerical method obviously converges better with some functions compared to some other nasty functions, right? But log normal is pretty nice looking. It's just almost like a skewed right normal distribution bounded below by 0, but it's nice generally speaking. So as long as the area underneath this curve is equal to 1, then we are safe, provided that this function is non-negative, which one can verify is. Now we can start doing some probabilities with it. So what's the probability that x is less than 3.5? So that's obviously going to be the integral of our function f of x on the interval 0 to 3.5. So lower is equal to 0, upper is equal to 3.5, and the probability that this log normal random variable is less than 3.5, or that a random person has a hair strand length of 3.5 inches or less is approximately 19.35%. If you want to do, for example, the probability that x is bigger than 4.5, you can do integrate fx and then lower is equal to 4.5 and then upper is equal to capital I and f for infinity. And we have 64.195%. And you can obviously integrate between boundaries quite easily. So the probability that x is between 2 and 3. That's just going to be equal to the integral of our function, lower bound 2, upper bound 3, and that's going to give you your probability value. Now, just as a side thing to note, you could have implemented the uniform, the exponential, or the normal distributions, provided that you know what the probability density function representations actually look like, and just use this integrate function to find those probabilities. And again, I mentioned there are ways that you can do inverse numerical integration to find quantiles, but we'll be talking about that in another video where we focus on solving equations. So for now, those are the basics of doing continuous probability in the R programming language. I hope you enjoyed this video, and I'll see you in the next one. Take care.